Hi, everybody. My name is Alejandra Lopez, and I am an assistant professor in the Physics Institute at the National University of Mexico. Let's share the presentation. Okay. Today, I will talk you about the influence of low-energy hydrogen ions irradiation on the optical, morphological, and structural properties of zinc oxide thin films. This work was made in collaboration with Professor Dwight Acosta, Professor Beatriz Fuentes, Dr. Carlos Magaña, Dr. Juan Lopez, and the undergraduate student Yacer Cruz. Let's start. The first thing we have to do was prepare the film. Zinc oxide thin films were prepared on a substrate of soda lime glass using the spray pyrolysis technique at 450 degrees Celsius. After that, irradiation was performed with 8 kiloelectron volts hydrogen ions at a fluence of 10 to 14 to 2 times 10 to 15, using for that a collectron ion gun. Structural, optical, and morphological studies were performed, and the results are the following. First of all, we have to make some Monte Carlo simulations of the collides between the hydrogen atoms and the zinc oxide films. Here we have the trajectories of the hydrogen ions after colliding with the zinc oxide films, and here we have the distribution of the ions in the film. We observe that most of the ions are implanted in the film. Two important things we have to consider are ionization and the collision events, vacancies produced during the collisions. When ions interact with matter, they do with two things, electrons and nuclei. When they do with electrons, we have ionization, and when they do with nuclei, we have vacancies or collision events. As a consequence of these collisions, of these ionizations, the material can modify the properties of it. So it's what we are going to see. If it's irradiation can modify the properties of the film. We also have to calculate the thickness and atomic concentration of the films. We made it by the EVA technique, Rutherford backscattering spectrometry, using the following conditions. We use the incident ion of particles, the ion energy of 2.5 megaelectron volts, an incident angle of 0 degrees, I mean, it was perpendicular to the target, and a scattering angle of 167 degrees. Here we have a typical RBS spectrum where we see the elements that compose the sample. For example, we have zinc and oxygen that compose the film, and silicon and oxygen that compose the substrate. Thickness of the film was calculated and was obtained using energy loss calculations. During a Rutherford backscattering experiment, alpha particles lost energy in different ways, depending on the atom they collide with or according to the depth the atom is located at. In this way, by calculating the stopping powers of the alpha particles in each element that compose the material, we can be able to obtain the thickness of the film using this equation. This equation shows that the thickness is related with energy loss of alpha particles and with the energy loss factor. The energy loss of the alpha particles is obtained from the spectra, the RBS spectra. Here we have the zinc peak, and this quantity is delta E, delta energy, that is the energy loss of the alpha particles when they collide with the film. The energy loss factor is calculated using this equation, where it's dependent on the kinematic factor, the scattering angle, and the stopping power. This is the stopping power of alpha particles in zinc. Okay, here we have the results after irradiation. Crystalline structure of the films was studied by X-ray diffraction analysis. Here we have the diffractograms of the films, of the as-grown films and the irradiated films. we can see that all of them are polycrystalline films, and they have an hexagonal structure and a preferred growth orientation along Z-axis, as we see here, before and after irradiation. We also observe that the irradiation is favoring crystal growth and improving crystallinity of the film, just as thermal treatments do with material. In our case, this effect of thermal treatment is due to a fast and local temperature increase. It is well known that during ion irradiation, thermal spikes can be produced and that these spikes can be compared to a thermal treatment, improving the crystallinity of materials. Another thing that we see in this diffractogram is that when we compare the as-grown and the irradiated films, we observe that the irradiated films shows a very small shift to lower angles. Here we see. And this shift could be a consequence of a microstrain in structure due to vacancies and interstitials. The optical results show this graph. We were interested in energy band gap, so we use a tog relation for an alloy direct transition, that's why this here, and we calculate the energy band gap of each of the materials, the as-grown and the irradiated ones. We observe, after we calculated it, we observe that the irradiated band gap energy have a reduction, and that this reduction in the band gap of the radiated samples is related to an improvement in crystallinity, as was observed in the structural result. It's also due to oxygen vacancies and zinc interstitials that produce changes in the crystalline matrix, which narrows the energy band gap. Morphological results doing with SEM microscopy show that the irradiation of the films allow the nucleation and the formation of grains that compose the films. The irradiation also changed the morphology of the grains, modifying the structure from grounded particles in the as-ground film to some of kind like flake-like particles in the irradiated ones. As a conclusion, we can say that the ion irradiation done with hydrogen can be used to tailor the optical, structural, and morphological properties of the material. This tailoring could be an important tool for optoelectronics applications. Thank you very much. Muchas gracias.